basically, sort of, it's the same thing, right? The only thing that we're getting with our hierarchical model is an R-squared change, so we can see the incremental increase in the total predicted variability of our outcome with the addition of sort of this block of scores and this block of scores, right? So, but if we're taking a look at our different components of our output, here is our simultaneous model with all of our 3 variables in there. Sort of this, my R squared is the same thing as my R squared that I get down here, right? So nothing magical going on, we're just sort of adding, building up. Same thing, my ANOVA table for my simultaneous regression is identical to, by the time I actually add all the variables in, all the predictors in that were in my simultaneous model. By the time I get to the end, it's all the same thing, right? There's nothing different going on here. Same thing with coefficients. These are my coefficients for my standard regression. And I go down to, when I finally get down to my full hierarchical model that has all my predictors in there, that's all the same thing, right? So nothing that's necessarily magical or different with our hierarchical models that we wouldn't get from our full regression models, outside of just, I can start to gauge what's the relative contribution of adding sort of this block of variables to the model, right? So I've got a regression model, I've got 2 predictors, and so these are just general sort of covariance, right? And then when I add in the 3 additional predictors that are actually sort of what I'm interested in, I can say that the addition of these additional predictors, these 3 additional predictors, increase the proportion of variability that I'm accounting for the output by 30% above and beyond sort of what was done previously, right? And if that's an important question, then do it. If it's not, then whatever, you don't need to do it. Again, this is just, I've had multiple times where people tell me, oh, you have to run this. It's inappropriate not to run this in a hierarchical regression model, which I then have to decide whether or not I want to pick and choose, have a battle with people on it because people think it's special and magical. Okay. Again, sort of Layla here's sort of stuff for Stata. Sort of a nice thing Stata will do is sort of go through and provide you. So here's my first block, my second block, my third block, change in R squared, some stuff there, but you can play around with that. So then they get us to stepwise regression. And this is what is the kind of magic, semi-magical thing. People get stepwise and hierarchical regression turned around. When we're talking about stepwise statistical regression, this is a model in which predictors are included or excluded from the model based with incremental association with outcome. So in this case, what I'm doing is I'm saying, here's a set of 10 predictors in my model. And what this is going to do, depending on how it's sort of, if it's an additive model or a subtraction model, what it's going to do is it's going to go through and it's going to say, remember that in our regression models that we've talked about, okay? If this is my, okay, these are my 2 predictors here, okay? Kate, if I go through what proportion of this Venn diagram do I get to credit for to IV1?
Anywhere, or just that one?
Just, which one?
I'm asking, so like, it's only IV1?
Yeah. Within the context of this model. So the coefficient for my first IV, what gets credit? What does this one get credit for? Which region?
Just that, like, yeah.
This one? Yep. Okay. What about IV2?
The same thing, but on the other side.
This one, right? Where does this piece go? Where does that get counted? Haley, do you know?
Is that just after you add both predictors to the model?
Yeah, so
accounting for it?
So we're kind of, so IV1 gets this, IV2 gets this. Where does this go? Does that not count, or does that get put somewhere?
Semi-partial correlation.
What's that?
The semi-partial correlation.
Okay, semi-partial correlation is going to be out here.
Wouldn't it be if you had the interaction term in
not the interaction term, because this is an additive model, we don't got an interaction in here. Here's my R squared, right? R squared is just what's the total variability that goes in, that's what's, sort of the total variability attributable to the best linear combination of my predictors, right? So if I'm looking at my outcome, this overlap is captured within the coefficient for my first IV, because this is the unique relation between my outcome and my predictor after I've partialed other stuff out. Same thing. This is the credit, IV2 gets credit for this, because this is unique stuff between IV2 and my DV that's not attributable to anything else, right? But here's our overlap. This is the stuff that's shared by both our, or the combination of our independent variables. This is shared variability between IV1 and IV2 that's also shared with IV3. This piece, we still want to count it, right? It's just no one gets credit for that uniquely, because it's not unique, it's just sort of total variability. And so this goes into our R squared, right? So our R squared picks up is the total of this, this, and this. IV1 is just here, IV2 is right here. But my R squared, my total variability, it's anything in this overlap here, okay? And so this is why, if I'm talking about my squared partial correlation, right? My squared partial correlation is interpreted as the proportion of variability unique to, in my outcome that's unique to IV1, right? Or IV2. I take that semi-partial correlation and square that. That captures the proportion of proportion of total variability in my outcome that I can uniquely attribute to IV1 or IV2 within the context of this model, okay? We also have a partial correlation. What is our partial correlation? If we were to square our partial correlation, which I don't often do, but what does our partial correlation tell us, John? What's the difference between the semi-partial and partial correlation? Yeah. Perfect, right? So it's both unique proportion of variability, right? But what happens, what starts to change is the denominator, right? And go back through, take a look at this slide. Semi-partial correlations, these are nice, these have good interpretive value, because it's saying, of the total variability in my outcome, what proportion of that variability is unique to IV1 controlling for everything else in the model, right? So of the total piece of the pie, what's unique to this predictor? That's what I get with my squared semi-partial correlation. Squared partial correlation tells me what proportion of the residual variability is attributable to my predictor, right? Here, instead of the total piece of the pie, I'm just looking at, so my partial correlation here is saying of this, of everything left over, actually after we section out part 2, right, what proportion of what's left over can we link to that first IV, right? So if this is area A, right, my semi-partial correlation is A over total, right? What proportion is this representative of all the variable in my outcome? Versus my partial is what's A over, let's say, total minus sort of the other stuff, right? So if I go through and I take, this is my total piece of the pie, and I say, how much the total piece of pie is overlapped with other variables that I'm not interested in, I'm gonna take that out. Of what's left over, what's unique to my predictor, right? So again, what we're talking about with our squared partial correlation, we're talking about our squared partial correlation as the proportion of residual variability that's attributable to my predictor after controlling for everything else, right? Semi-partial is a proportion of total variability that's unique to my predictor after accounting for things, right? So it's the denominator that's changing across this. So again, there's slides that we went through in the regression model that go through and sort of section that off that Venn diagram. Probably one of the most useful diagrams I've ever sort of came across in my life in helping me sort of conceptualize what's going on within these regression models. Okay. So if this is what's going on in my standard regression, what's going on with my statistical regression or my stepwise regression. Okay, so here we go. I got two variables in my model, and I've got a stepwise regression, right? Within this, what I'm going to do is I'm going to go through, take a look, and whatever variable, IV1 or IV2, has the greatest, whatever variable has the strongest correlation with my outcome, whichever one of these has, like, in terms of absolute magnitude, whichever one of these has the strongest relation with my outcome, what variability is that, what regions does that get? It's, in a stepwise regression, it's all of this, right? IV1 was the bigger hitter, and so all of the variability in the outcome that's shared with IV1, that's what IV1 gets, right? If IV2 would have been bigger, IV2 would have gotten all that, right? And then what we go through is we then systematically go through and take a look at, so the predictor with the greatest absolute correlation entered first, and then subsequent variables added or subtracted based on sort of the relative contribution. So if I've got let's say a third variable in here, that's here, right? And this one is the second amount, then this gets all of that. Or actually, and then let's say I've got another one that's here, right? But this has more than what's left over, then this gets all of this, right? So by the time we get down to the end, IV2 now no longer has much of anything there. Now it does, right? Now if we sort of hadn't gone through and started sectioning things out, but now we've started to eat into this stuff. And so what ends up happening with our statistical regression models is that if eventually we get down to, all right, predictor 1 has the most, sort of in the bivariate relation, so this has the highest correlation with my outcome. So everything that's shared there gets chalked up to that. And then what's left over, predictor 3 has the next biggest, so then that gets everything. And then predictor 4 has the next biggest, that gets everything that's left over. And then predictor 5 is just kind of left out in the sort of dust because there's nothing left over there for it to predict in, right? So predictor 2 gets pitched out, and so our model says predictor 1 with a huge component, 4 with a smaller one, and 3 with a smaller one than that, and then 2 is sort of SOL on this situation, okay? And so what you'll see this is in business, marketing, econ sometimes, so these, where we're trying to predict outcome, right? We have no theoretical idea of what's going on. We're just trying to maximize the variability in our predictive value of our model. And I've got a massive data set, and I've got 100 different predictors. What I'm going to do is I'm going to drop these into a stepwise regression, and I'm just going to say, what's my model? What are the ones that are accounting for the most? Cut that down, and that's just going to be the model. Okay. So our stepwise or our statistical regressions are completely data-driven models. Like I have no control over what goes into my model outside of what's in the first big hopper that I drop down into there. And then once that's going down, we're making decisions based on the absolute magnitude of correlations for sort of how things start to play out. Okay. Now this is mathematically, conceptually controversial one, particularly within our field, because there's no theoretical basis for this, right? It's purely a data-driven. This data set that I have is determining what goes into and sort of gets included or kicked out in terms of a predictor. So the big concern with this is that our final solution is very sensitive to sample-specific stuff, right? So, Evelyn, I've got sort of in this sort of example, sort of these two correlations. So this is a correlation with my outcome of 0.34, and this is 0.341. Which one of these gets all the shared variance between all of them?
Maybe 2.
The 341, right? Is it very clearly that this is a better predictor, or is it no, right? If we run another sample and this turns around, now all of a sudden IV1, the biggest hitter in our first model, doesn't even include it in the other model because it got kicked out because this one was bigger and then everything else went through and sucked everything else up, right? So we have problems in terms of the variables that start to sort of be prominent in these models, often very specific to the nuances of the data set that I'm looking at, is we have a hard time replicating. Now sometimes if this is very clearly sort of taking up the biggest piece of the pie, it's going to sort of keep going in, but the model or the specific variables that are included in that model might jump around wildly just based on minor trivial differences in terms of the absolute correlation of my predictors and my outcome. And this is a bad thing for us because we're typically focused on theoretical relations and sort of what should be in and out. And what we end up do, we end up overfitting the data, right? This model is very good at predicting and maximizing the variability in this data set. But if I took the same model and applied it to a different data set, it might be kind of crappy, because what we just did is we took advantage of all just sample-specific characteristics of this model that don't necessarily generalize to anything else, right? Same type of thing. We're talking about looking at linearity of predictors, right? And saying, oh, do I have a nonlinear relation? If I'm seeing some sort of pattern, is this something that's true and characteristic of sort of the population, the relation between these constructs and the population, or is this just a kind of a weird thing that's kind of looking like a semi-curve within my data, right? And so not wanting to overfit your model to your data for the things that we're looking at. We're looking at things that are generalizable, that capture sort of the underlying sort of mechanisms and theoretical components of our different stuff. And so what we have is there are solutions, or there are procedures for best practice approach to stepwise regression, but you will likely not see this within our field just because it's not consistent with what we're trying to do, right? If I've got my business and I'm trying to maximize and project like sort of what my year profits are, and I just throw everything I have into the hopper in sort of this in this stepwise regression to just try and sort of maximize for my specific business, maximize what my earnings are going to be so I can budget for the end, fine, whatever, right? But that's not typically what we're trying to do in psychological science. And so always be very wary. One, you'll probably never use these. And if you see them in the literature, be very careful about sort of interpreting sort of some of these effects and stuff. These things in one model that might be super important might not even get included in the next model just based on small deviations in terms of sort of correlations and stuff like that. So people kind of see why people hate on these stepwise models and why we don't see them so much in our field. Okay, cool. So last thing, in terms of practical issues, always think about your model selection. We talked about this, right? Proper specification is an underlying assumption of our regression models that we don't think about a lot, right? And oftentimes it's just because we're come across some data, right? So Layla's going to write a paper, and so we've got lab-based data, and I want to look at this and that. And there's only so many things to choose from, right? But still, even if that's the case, wanting to think about the extent to which our models are valid and good and sort of generalizable, a direct function of sort of the quality of variables that we've included, and sort of making sure that everything that should be in there is in there, and things that don't need to be in there are not in there. There's no statistical fix. Like, I can't go through and you say, oh, well, I measured this measure that doesn't actually measure what I want to measure. No, you just have a bad measure, right? And so again, wanting to make sure that sort of the stuff that we're putting in are good measures, they're valid measures, they're reliable measures, and sort of recognizing that our regression models are at their very best when I have a set of predictors that are maximally associated with my outcome and minimally associated with one another, right? Those are my most efficient models, because if I've got up with this guy. So here's my DV. This is what I'm trying to predict, right? So my best regression model, so here's predictor 1, right? This is IV1. My best predictor in my additive model, IV2, right? This second predictor I got in my model is just getting all the stuff that IV1 missed, right? This is best, right? Everything's related to everything in our field, and so we don't often get this, but if I add a variable that is associated this with, I don't know, I got something in the model that's just basically just doing all the same stuff as the first one did. It's not going to get hardly any unique contribution here. My best model is going to be those ones where I've got, here's my predictor, counting for stuff. Here's my second predictor, counts for a whole different unique component of whatever it is I'm trying to account for. And then my third model, and my third predictor over here, getting at a completely other aspect of things. So it is this additive idea that each one of my predictors are adding something new and unique to the prediction of my outcome. These are going to be our most efficient models. Again, our goal should be to identify the model that does the best and accounts for the most of what it is I'm looking for with the fewest predictors. When we start to get problematic, or when we start to have problems, is here's my outcome, right? And I say, okay, well, I need to know I need to have variables in this model, because as I sort of do a better job of increasing my R-squared, as I do a better job of predicting variability in my outcome, it makes my model stronger for my individual predictors, right? So the higher my R-squared is, the more powerful my model is, because I'm sort of taking out all that error variance, right? What happens sometimes, if we're not being careful, not thinking about things closely, is what I do is I say, okay, well, here's this. But then I'm going to throw in this other construct that's going to do this. And then I've got another construct that I'm going to throw in, and it's going to be this, right? Now all of a sudden, if I'm a clinical person, I've got depression, anxiety, experiential avoidance, anxiety, sensitivity, and negative affect in my effort to maximize sort of my predictive value. But really, all four of those things are all measuring basically the same thing and not getting at anything unique. Like the stuff that I'm not getting with the first one, I'm not picking up anything except for like small amounts with these other things, because these are all overlapped on top of one another, right? Now this can be hard to do, but if we start thinking about correct specification of our model and thinking about what do we know about this construct, what are the different aspects, components that make up this phenomenon that we're trying to account for, and now let's go and try and grab some predictors that get unique characteristics, aspects of sort of this type of thing. That's going to lead us to much, much better models that are one, having higher R-squareds, but also getting unique components. So I've got unique predictors versus a situation like this, where I might have with the addition of these 3 additional predictors, I might have marginally higher R-squared value, but now none of my individuals are predictors are statistically significant. How does that happen? What do you think? So I've got my overall, so let's say my overall R-squared is 0.5, okay?
very clearly going to be a statistically significant model, right? I'm saying the best linear combination of my 4 predictors is accounting for 50% of the variability of my outcome. That's pretty good, right? When I go down through and I take a look at my individual predictors, none of them are statistically significant. What's going on there?
Is that one of those suppressor?
What's that?
Suppressor effects, where they sort of are taking, one of them is taking away maybe the variance?
Well, it's taking away variance, but it's not a suppressor issue. What's my issue here? Yeah.
Just that, like, one of those contributing.
Yeah, this is multiclinearity, right? I basically have 4 predictors that are all correlated like 0.9 with one another. They're doing a good job together in terms of capturing variability in my outcome, but individually, none of them's predicting anything unique, because I'm basically put the same measure in there 4 different times, and so now they're all super overlapped, right? So if I'm going through and trying to identify, sort of for this one here, there's nothing unique. Here I've kind of got this piece, here I've kind of got that piece, but those might at the end of the day be slivers. So basically, so this would be a classic indicator of massive collinearity, right? I've got a significant regression model, right? My sort of best linear combination of my predictors is accounting for a good deal of variability in my outcome, but none of my individual predictors are statistically significant. And my individual coefficients are telling me what's the unique relation between my predictor and my outcome. Well, there is none, because it's all basically the same thing. And so all of the variability that's being shared is just going straight into R squared, because none of these predictors are going to go through and account for anything unique or statistically significant. Okay. So again, this is really important when we're thinking about partial effects and sort of unique contributions of our predictors in our model and things like that, trying to tie all this stuff together. Okay. Does that help? Okay, cool. And then other thing we worry about sometimes is sample size, or a lot of times like how many cases do I need? How many variables do I need to run this, or how many people do I need to run this model? That's a complicated question. It depends on a lot of things. In general, bigger samples are always better than smaller samples. How many people do I need? As many as you can get. Particularly if we're starting to work, we'll look at interactions and things like that. Lots and lots. The more, the better, right? If we're looking at sort of trying to get, you'll see rules of thumb, right? Like, oh, you need to have 3 cases or 5 cases for every predictor in the model or something like that, or 10 times 2 the number of predictors times stuff. At this stage of the game, that should not be your approach. If you really want to get a specific number and you're trying to see, like, what do I need to adequately power this, run your power analysis. That's what you need to do, is you need to run a power analysis. Because the number of observations that you're going to need is going to depend on the number of predictors you have, although this actually contributes very little to your power. But anticipate your effect sizes of sort of mostly your R squareds, alpha levels, sort of all the general stuff that we think about that goes into a power analysis. So I can't just tell you, oh, how many people do I need for this model with 3 predictors, but I don't know. How well are those predictors related to your outcome? What's your R squared in your model? Sort of a lot of different things, right? In general, we know that we need larger samples when we have a dependent variable that's skewed, right? If we have an outcome measure that doesn't behave properly, we need more people. If we're looking at predictors that account for only a small proportion of variability in my outcome, I need more things. If I have questions about the reliability of my predictors, remember, basic assumption of my regression model is that I've measured my predictors without error, right? And remember that my regression coefficient here is going to be equal to sort of my population coefficient times my alpha, right? And so as this starts to get smaller and smaller and smaller, sort of it makes my actual estimated effect. So let's say my actual coefficient here is 0.80, right? The smaller and smaller, the worse and worse my reliability on this gets, the smaller my estimated effect is going to be, just as a function of this being attenuated because of my
poor reliability, and so if I've got measures that are semi-garbage and aren't internally consistent, or to have poor test-retest reliability, it doesn't do a good job of measuring my outcome, that's going to mean I'm going to have to get more and more people in my sample. We're going to talk about that. This starts to become a particularly big issue when we're talking about interaction effects, because the issue there we had goes through the roof as soon as we start multiplying variables with one another. Okay. So just wanted to make sure that we get through this. Think about sort of things to keep in mind as you're going through approaching regression analyses and things like that. Okay. Questions on any of this stuff? Cool. All right. So let's switch over and start talking about moderation stuff. Before we jump into moderation, questions about our problem set that we have coming up?
Are you going to go through the example handout on the standard hierarchical regressions?
No. I mean, you go through on the sort of, that's just basically the same stuff that we went through there. So just go through, take a look. I mean, it's just basically running regression models, and everything's laid out. You guys should have a handle on that. Okay. There was a specific question on those?
I thought it would be helpful to see how you were interpreting all these results. Because sometimes when you do these, like the examples, you'll talk us through like how you might write it up.
Okay. Yes, we'll go through. We'll get lots of that in today's lecture. That should help out with that stuff. Does that help? Does that work? Okay, cool. Other questions about how our assignment came up on Friday? Yes.
So typically for effect sizes, when you ask us to interpret them, it's like pretty substantial interpretation. For interpreting the effects for the regression, it doesn't seem as though there would be like too much to say.
Yeah.
Okay.
Yeah. No, this is pretty straight. And I would hopefully don't think about like sort of your interpretation of effect sizes pretty substantial. I mean, for mean-based stuff, you're talking about sort of a, like sort of X scores and sort of half standard deviation above the other thing. But yeah, some of the stuff that we went through, I mean, is just pretty straightforward in terms of, and we'll talk more as in this lecture about sort of nuances in how we're looking at like different effect sizes and things like that. And I can give you some ideas on sort of when to present, what not to present. For this assessment, or for this, right, so we really just talked about squared semi-partial correlations as effect size, so just worry about that.
Okay.
Sound good? Mm-hmm. Cool. Other questions? All right. Cool. So we're going to go through today exciting stuff. Talk about sort of moderation, conceptual framework of our moderation. Going to talk about centering. Going to get to multiplicative models, and then that's probably as far as we can get today. So just kind of laying the groundwork for how we go through and within the context of a regression model start to look at some of these interaction effects. Okay, so we've talked about our regression models, right? Our standard regression models, or our hierarchical models, basically what we're looking at within our multiple regression models is what is the unique relation of these individual predictors with our outcome within the context of this model, right? So after we control for 1, 2, and 3, is there a unique relation between this predictor and the outcome controlling for other variables in the model, right? And this is just getting back up at this. What's the unique relation? What's the sort of, does this share unique variance after we partial other things out, right? And so these are nice because this takes us beyond just bivariate correlations, right, where we say, oh, X is related to Y. We can say, well, is X still related to Y once we partial out common variability associated with these other things, right? But after a while, and if we replicate this again and again and again, this starts to become less interesting and novel, right? For example, in my area, if you ask, say, Layla has the question, hey, is social support associated with PTSD symptom severity? The answer is yes. We've got meta-analyses that say, yep, it's not as big as we would think it is, but yes, there's a consistent relation there. And so Leila comes up to me and she says, hey Josh, so I'm thinking about writing a paper for publication this summer that looks at whether or not social support has a unique relation with PTSD. I say, well, we probably need to think about that because that's not interesting anymore. We demonstrated this over and over again, right? And so with our standardized regression models, we start to get that does X hold a unique relation with our outcome? Maybe that's interesting if no one's ever actually looked at this before and we have a good theoretical reason for it. But if we've demonstrated this over and over again, that's sort of boring and probably not going to get you published, right? We're also limited in with our standardized regression models in sort of the nature of the relation, right? It's just like, is there a direct effect of X on Y after we control for other things, right? All we can say within our standard regression models is X2 hold an association with our dependent variable after we pull out other stuff, okay? And that's going to be a valuable thing, but it's kind of limited in sort of what it actually tells us about how these variables are related with one another. So once we've established over the course of maybe several studies that we do have a relation between X and Y in the population, right? One thing that we can start to ask that sort of spices things up a little bit is we can say, okay, so I see across studies that X is related to Y controlling for other stuff, right? Maybe what I want to say is that relationship consistent? Is it the same association? Do I see the same effect of X on Y controlling for other things across all incidences, across all populations? So what are the boundaries for this association? Is this forever and always the end all be all? The population association between X and Y is always 0.3, or are there situations, or are there other variables that start to change the magnitude or direction of this relation, okay? And so if we're asking, if we start to think about sort of under what conditions, what types of things might change the strength of this relation or the direction of this relation, we're talking about moderation, okay? Because if you think, I dare you to come up with some variable that holds a relation with an outcome under all circumstances, under all universes, under all possible realities that could ever come to be under any other, all circumstances? No, right? There's going to be certain things that change the nature of how John and I relate to one another, right? John and I our relation might be pretty similar, right? But there are going to be things that come in that start to strengthen, weaken, sort of go through and change the nature of that relationship. And this is what we're talking about with our moderation question. What are sort of looking at the processes in which some external variable starts to change the nature of the relation between X and Y, right? What factors, what situations, what circumstances, what other characteristics start to influence sort of the strength, the magnitude or direction of this baseline relation, okay? And so again, when we're talking about a moderator, this is typically how we go through a diagram, a moderated relationship. Our moderator is going to be any variable that impacts the magnitude or direction of sort of the relation between X and Y, okay? So the idea is like, X is related to Y, X is related to Y, X is related to Y, X is always related to Y. We consistently see X related to Y, and maybe now the question is, what are the things that start to change the nature of that relation? What makes it stronger, what makes it weaker, what might even actually flip around the direction of that association, right? So some examples of some hypotheses, right? I want to look at the impact of stress on physical health and whether that depends on degree of social support, right? Stress related to physical health, stress related to physical health, stress related to physical health. Well, what if we start changing the level of social support this person has? If we have more or we have less, what does it do to this relationship, right? And so what we're looking at, sort of our outcome here is the magnitude of this relationship. Does this thing, if I start to flip around sort of levels of my moderator, does it change the magnitude of this association? Okay. What is the relationship, what is the relation between psychological stress and problematic substance use across men and women, right? We know that distress has an association with substance use. If I get worked up, I use substances. If I get worked up, I use substances. But does that relationship look different if we're talking about men versus women?
Or is it the exact same across these two? Maybe men and women have, the relation between psychological distress, problematic substance use is exactly the same. Or maybe it kind of looks different for one group or the other. Maybe for women, maybe for men, this is a strong relationship, right? Stress, substance use is coping. Stress, substance use is coping. Maybe for women, that relationship is actually much weaker, right? So we see it really strong in one group, but actually not so strong in another group, right? These are the types of things that we can start to see. Looking at conditions in which some association is strengthened or weakened, right? And if we do find these moderated effects, we're going to say that the relation between X and Y are conditioned on level of the moderator. Okay. Where we talked about conditional effects before. What's that? Factorial and over, right? We're saying, what's the difference between these two groups? Well, I don't know. I have to know whether or not we have some other thing going on, right? Again, we're going to be talking about interactions here, and so anytime we're talking about effects within the context of a significant interaction, we're not talking direct effects anymore, we're talking about conditional effects, right? And you say, what's the relation between X and Y? I say, boy, I can't tell you. I need to know what M is. If I know what M is, then I can tell you, right? But in the absence of that, I can't tell you exactly what the relation between X and Y is because it changes depending on them. People sort of wrapping their head around sort of what we're asking with these models and what we're doing with this. Okay. So if we go back in our history, these interactions between our categorical variables, we've typically, historically, in the history of psychology, have used ANOVA models to go through and take a look at these types of things, right? I'm looking at the interaction of gender and ethnicity on social bonding, or I'm looking at the interaction of condition 1, factor 1, and factor 2 that I've manipulated with an experimental design on some relevant outcome, right? But what happens is sometimes we want to look at sort of the other factor, the other variable we're interested in is something that's continuous, right? Something that doesn't break into categories, right? And this is where our ANOVA models start to fall apart, right? I want to look at the interaction of ethnicity, sort of people identify black, white, and SES on institutional salary, right? This is an important question, sort of getting at systematic bias, discrimination, and things like that, right? But I've got SES that's hard to, so what do I do with that? It's a continuous variable, right? Historically, what we've done is we've gone through and used median splits, right? We've taken this continuous variable and we say, all right, here's the median, everything above is this, everything below is this, and now we've taken this continuous variable, we run a median split, we turn it into a dichotomous variable, and so now we can go through and now we can run it in our ANOVA model, or our ANOVA model, okay? Problem is, if we do this, it typically results in losses of power, right? Basically, we've said, here's my distribution. That's worse. Here's my distribution. Here's my median split. I'm saying everybody to this side of the line is the same, everybody on this side of the line is the same, right? This is clearly problematic, and then we've got the majority of people who we've said are different are actually quite similar, right? And so what we do is if we're treating everybody on this side as the same, everybody on this side is the same, we lose a lot of statistical power because we're just sort of grouping people in groups that don't belong in groups. And what we do is we lose power in our models to go through and identify things. And then probably the worst things is we start to introduce the potential for bias effects, right? We've artificially dichotomized in a semi-random fashion, in an arbitrary way, something that's actually continuous. And when I force it to say, okay, this is everybody that's high, everybody that's low, what I start to do is oftentimes get weird effects that don't actually reflect reality, okay? Today, there is no reason to median split anything. Median splits are terrible. We just have too many other options. If I were to review a paper where anybody did a median split, I would be like, don't do that. Just sort of use tools that are appropriate for capturing the continuous nature of your variable, right? And this is going to be our regression models. Our regression models, what we can do is we can start to look at interaction effects between any combination of categorical continuous variables without splitting things into dichotomies, right? We're going to go through and utilize the full information available on this continuous variable and see whether or not this interacts with some dichotomous variable. And so what we're getting is a full range of information without artificially splitting things into groups that don't belong with one another, right? And we can actually do this pretty easy. We've got a lot of, well, I want you to, it's not easy. There's some steps, and you need to understand sort of exactly what's going on in here. But the thing is, the tools we have available at our disposal sort of make it very hard to justify sort of going back into our history and using some of the other tools. At the time, it was the best we had available, right? We didn't have good computing systems, and sort of regression was difficult and things along these lines. But now, sort of pretty slick and easy to be able to go through and sort of run some of these models within the context of a regression. Because remember, ANOVA, just a special case of regression. There's nothing that we can do in an ANOVA model that we can't do within the context of a regression analysis, given proper coding of our variables and things, right? So we're going to continue on with the same example set that we had used before. We're going to pretend that role functioning is actually a reasonable outcome and not a categorical one for the purposes of this, just to simplify things. So this is the same one we went through and did the screening on and decided that a regression analysis wasn't appropriate given the measurement of our outcome. We're going to ignore that and pretend that that's not the case, and sort of use this to go through and look at some multiplicative models here. So we've got two hypotheses throughout these examples. My question is, does opiate medications influence the impact of physical pain on role functioning in survivors of serious motor vehicle accident, right? So the question is, I know that physical pain has a direct effect on role functioning, right? As my pain goes up, what happens to my function? It goes down, right? This is very obvious, this is very consistent, right? But maybe my question is, what about people on opiates, right? Like, these are painkillers, these are things supposed to help manage pain. Does this help? Does this increase functioning, right? Does taking opiate medication moderate or influence the association between pain severity and global functioning? Okay. Other question is, I also might want to know whether or not pain severity changes the relationship between PTSD and role functioning in accident survivors, right? So I know, again, very clear, it's not interesting. Is PTSD associated with functioning? Yep. As my PTSD goes up, my functioning goes down. That's not an interesting question, right? What about if I throw in chronic pain? Does chronic pain change the nature of that relationship, right? Does the relationship between PTSD severity and role functioning, does that get stronger or weaker depending on the level of severity of pain, chronic pain that individuals are experiencing, right? So we will see, so thinking about our moderation questions in terms of a base relation, all right? What's the base relationship? What's the thing that's kind of there? And then saying, what's the third variable that might go through and change the nature of that association? And so here again, we've got indicator of continuous pain. Opiate use is dichotomous, yes, no. PTSD, continuous severity of PTSD, and then our role functioning, range 0 to 100. It's actually not, it's a terrible sort of ordered categorical variable that sort of gives us a lot of problems, but we'll pretend that we don't know that for right now. People get a handle on kind of what we're trying to think about here. Okay. So, I'm going to take a quick detour. One thing we haven't talked about to this point is centering, right? As we've gone through our regression models, we've just said, all right, here's X1, X2, here's opiate use, pain, PTSD, right? And again, so if we could go through and take a look at your
do you have your output for that regression model? Yeah.
For today?
For the last one. Never mind. Here, Laura has it. I know. So teach you to ask me questions. All right. So here I've got an association right here that says pain severity is associated with role functioning. Right. It's a statistically significant effect. Give me an interpretation of that unstandardized coefficient right there.
For every 1 unit increase in pain severity, there's a 0.68 unit decrease in role functioning. Controlling for where we have their opioid use.
Yeah.
PTSD.
And from a mathematical standpoint, what does controlling for opiate use in PTSD mean?
It's removing the variance.
Yeah.
Contributed by
But holding it constant at
0.
okay, there we go. Within the context of our regression model, 0 holds an important place, right? So what I'm saying, so I've got a coefficient here of 0.685, okay? Negative 0.685. And technically what this is saying is for every unit increase in pain severity, I'm expecting a 0.685 unit decrease in role functioning, holding opiate use and PTSD total score equal to 0, okay? And sort of from my regression model standpoint, if I've got role functioning is equal to minus 0.39. And we can start to see this in terms of our mathematical model, right? Nick, tell me what this number is.
That's your liner. So basically, what everything else is equal to 0.
Yep.
That's what your value.
So this is my expected score for role functioning if I were to hold everything else, controlling for all of the variables in the model, or holding everything else constant at 0, right? So I plug 0 in this goes away, 0 goes away, 0, that goes away, okay? But how about this? Kate, what does it mean if I'm holding opiate use constant at 0?
Then, so I guess you're not taking that into account when you're looking at pain and PTSD.
I kind of am, though. What does 0, if I have a 0 on opiate use, what does that mean? If it's a dichotomous indicator.
But they're not.
Then I'm not taking opiates, right? And so literally what this is saying, if I'm looking at, so we're looking at the coefficient for pain, right? I'm saying if I wanted to sort of get sort of long about this, I would say that I expect for every 1 unit increase in pain, I expect a 0.685 unit decrease in pain, holding for individuals not taking opiates, holding PTSD scores constant at 0, right? Because this starts to get into our dichotomous sort of thinking literally about what does it mean when I'm holding variables constant at 0. It doesn't, well, it means they go away, the term goes away, right? But if I'm holding opiate use constant at 0, that just means people were taking opiates, right? But this is completely arbitrary. What if I recoded this? 0 means I'm taking opiates, 1 means I'm not taking opiates. Now all of a sudden, this is telling me the relation of sort of expected change in role functioning given a unit increase in pain for people who are taking opiates. If opiate use is 0, I'm using opiates, on 1 I'm not, and sort of PTSD held constant at 0, right? And so as you start to go through and work with these regression models, particularly within the context of moderation, and then if you're getting into HLM stuff, like that 0 point starts to become very, very, very important, right? And so wanting to think about what does 0 mean, and a lot of the manipulation we do with these models involves changing that 0 point around so that it means something, okay? So for this model, I can have opiate use as 0, that just means I'm not using opiates. I can have pain at 0, that just means I'm not having pain. And I can have PTSD at 0, that just means I'm not having any symptoms, right? But what if we're talking about looking at the relation between the association of trying to look at weight equals intercept plus height. Okay. So here, I've quoted sex 0 female, 1 male, right? And I'm looking at the prediction of weight with, I'm looking at, say, sort of the coefficient for sex is John, what does, and if women means 0, men equals 1, give me the interpretation of my coefficient for biological sex here.
Just do that for women, since it's code 0, it doesn't affect your outcome.
Okay, think about this, all right? What does it mean if I have a 1 unit increase in biological sex? What does that tell me?
You're male.
What is it?
That you're male.
That I'm male. And so I've changed from 0, which is female, to 1 is male, right? So if we're thinking about this, so I'm saying that I expect, oops, oh, that was terrible. And I've got weight in pounds here, okay? What I'm doing is I'm saying I expect, given a unit increase in biological sex, I expect a 20-pound increase in weight. But what does a 1 unit increase in sex mean? What am I talking about, Emilio? I've gone from woman to man. Right now, we don't, probably not relevant to sort of this model individually, but what does this coefficient represent?
It'll just be the increase from the constant.
Yeah, it will be. So you're on the right track. This is just the average difference in men and women controlling for height, right? This is just a mean difference. Like basically what we've done here, we've got an ANCOVA model, right? This is telling us the mean difference in weight across men and women controlling for height. Okay? And so with our categorical variable, with our dichotomous indicator, this is just an adjusted mean difference, right? So I'm saying that on average, or holding, now this is the trick, holding height constant at 0, I expect a 20-pound difference between men and women. Okay? Because that's what it means if I'm going from 0 to 1. I'm just talking about the difference between women who are 0 and 1 are men, right? And so this regression coefficient is saying, if I'm interpreting it literally, I'm saying holding height constant at 0, a 1 unit increase in biological sex is associated with we would expect a 20-pound increase in weight, right? Well, going from 0 to 1 just means I'm talking about men versus women, but then this starts to get tricky. What is holding height constant at 0? Can I hold height constant at 0? 0 is not a real value for height. Like I can't have a height of 0, right? But this is what my regression model says. It's giving me the estimated difference between men and women holding height constant at 0. But height, that's not a real value that it can take. And so we start to worry about sort of what ends up happening is this doesn't fit in our understanding of these constructs, right? And so again, here it's fine because I can sort of, so again, this reflect.
For every 1 unit increase in opioid use, role functioning will decrease by 0.39, holding everything else constant.
At 0,
Yeah.
right? Okay. But because opiate use is dichotomous, what is this actually telling us?
That if you go from no opiate use to yes opiate use and holding everything else constant, that's how much your role functioning will decrease.
Right, right. So basically we're talking about the mean difference in role functioning for people who are taking opiates and those who aren't, controlling for other things in the model, right? And so this, when we start to remember with our regression models, I'll start waving this around, I'll do that back to you. When we're thinking about interpreting our regression models, so this 0 point starts to become important, right? Our dichotomous indicators are just giving us mean differences, right? And so we're holding everything else constant at 0. But what ends up happening is in some cases, 0 doesn't necessarily mean anything. But what we can do, if we go through and center our variables, what we're doing is we're rescaling our continuous variables so that 0 now has an intuitively interesting and relevant meaning. What we're going to do is we're going to go through, to center our variables, we're going to go through our entire set and we're going to subtract each score, subtract the mean of that variable from each score in the set, okay? So we're going to just take X values for each person and we're going to subtract the mean. So if I'm just going to center PTSD here, I would just take PTSD score for everybody and subtract the mean value of PTSD. Let's see, the mean value is 30, right? So I'm just going to subtract 30 for everybody. And what that's going to do is that's going to recenter. So my new mean of this variable, what's the mean of my center variable going to be? 0. It's going to be 0, right? And now 0, instead of saying, so this is a relation between if these variables are centered, right? I'm saying that this is the difference in people who are using opiates and who aren't using opiates, holding pain and PTSD constant at the mean, right? If these are centered values, all of a sudden 0 just means the mean, right? Now this is different than standardization, right? So we're not standardizing, because standardization, if we're calculating z-scores, then we're dividing by the standard deviation, right? And we're not changing the scale, we're just taking the whole distribution and shifting it around, okay? So let's say here's my uncentered variable, right? I've got a mean of 5.6, a standard deviation of 2.3, okay? And so Haley's at the mean. She has a value of 5.6, okay? But what I do, and so this is my uncentered distribution. What I do is I want to center that distribution. So I take all the values, all the sets in my score, and I subtract 5.6 from them, right? Haley's right here at the mean at 5.6, but Kate's down here. Kate's real low in whatever it is we're talking about here, right? It's probably regression. We go down through and we subtract the mean from all of these variables, right? We've got a new distribution. Distribution still looks the same, right? Haley is still here at the mean in the center of the distribution, but your score now is 0. Kate's score, she's still at the same point in the distribution. Your score is now just negative. If you were 0 before, now your score is negative. What is your score now?
Sorry, it's just negative.
Negative what?
Oh, whatever the mean is.
Yeah, negative 5.6, right? So we've just gone through, it's the same distribution. All we're doing is we're just making 0 the mean value, right? And we're just doing that by going through and taking every value in the set, subtracting the mean from that, okay? And so the benefits of our centering procedure, one, it's going to make our models more interpretable. It's going to improve the interpretation, right? So now I'm not saying this is the difference in men and women in weight holding height constant 0. We're still saying, yeah, the model's still holding height constant at 0, but now in our, if we're using centered height, a value of 0 just means the mean. It doesn't mean the absence of height, right? The absence of height is not a construct I understand. But mean height, that starts to make some sense to me, okay? It's going to help with the calculation of our interaction effects. And what it's going to do is it's going to start to address some issues of collinearity. Now, this doesn't impact your model at all or the results that you're going to get. And there's starting to become a sort of movement where people are like, oh, you don't need to center your stuff because it doesn't do anything to your model. And that's true, but it makes it easier to interpret. And there are starting to get into like SEM types of things. That'll sort of crash your model if you start getting collinearity between interaction terms and things like that. So primarily what we're doing when we're centering our models, we're making things more interpretable, and we're helping as we're going through calculating interaction effects. Okay. So centering is pretty easy in SPSS. You're just going to hit compute, centered variable equals whatever my variable was minus whatever the mean is. Now I've got a centered variable. Easy peasy. Okay. All right. So when we go through and we center, no impact on the shape or variability of the distribution. Variability is the same, shape of the distribution is the same. We just took that thing and just slid it around so the middle of the distribution is now equal to 0. Centering doesn't impact correlations or regression coefficients in models that don't have any interaction effects, right? If I look at the correlation between my centered variables and my uncentered variables, identical. If I look at the coefficients for my centered variables and my regression coefficients for my centered variables and my uncentered variables, they're going to be identical, with except for the intercept, right? Because again, remember, this is my expected value of role functioning when opiate use, pain, and PTSD are all held constant at 0, right? Now, if I go through and center these, let's say I center pain and PTSD, now this is going to be the expected value of role functioning when pain is at the mean and PTSD is at the mean. And that's obviously going to change my expected. My intercept is going to change, right? Because if PTSD and pain are equal to 0, what do I expect role functioning to be? Pretty good, right? If I'm holding PTSD and pain constant at the mean, if the mean is now 0, functioning at the mean of pain, the mean of PTSD is probably going to be worse, right? So your intercept is going to change. But your actual regression coefficients for your predictors, correlations, these aren't going to change, okay? Unless we have interactive effects in the model. If we have interactions in the model, centering is going to start to impact the coefficient in your models, except for your highest order interaction term, right? So if I've got a model with a two-way interaction is going to be the same no matter whether I'm using center variables or not. If I have a three-way interaction, my three-way interaction is going to be the same whether I have center variables or not, but then my two-way interactions are going to have different coefficients. And my direct effects or my conditional effects are going to have different sort of things. Or if I just have a two-way interaction, then my sort of direct effects or my conditional effects are going to change around whether I center or not, right? And we'll talk about why that is in a moment. But what we see is our simple slopes that we'll talk about are unaffected. Shape of your simple slopes are unaffected. So this starts to become important. This isn't just like FYI bar trivia, stuff like that. There's a lot of steps that go through with these multiplicative effects, right? As we're running our regression models, there's a lot of different things you're going to want to be keeping an eye on, and you're going to screw these up, right? It's just going to, I continue to screw them up, right? I'll forget to do something and then everything's off base. These are ways to go through and check to see, is the model turning out the way I expect it to be? If I've done it correct, this should be the same. These should not be the same. This is a way to go through and double check your model to make sure everything's working out the way it is. Never, ever, ever take your moderation analyses by just on faith, just assume that you did it right the first time. You probably won't. I still screw it up sometimes, right? And I have to go back through and sort of double check, is everything else playing out right? This is going to be one way to go through and take a look at stuff. Questions about this? All right, so let's go through and sort of thinking about our multiple regression equation for, okay. Let's take a break. This is a good stopping point. Be back here in sort of under 10, and we'll jump back into stuff here.
ahead. Okay. Questions about centering stuff and what's going on here? Okay. So again, the big thing is remember that anytime we're interpreting results of our regression model, the model itself is saying, so this is the expected, or so this is a unique relation of x and y, holding everything constant at 0. It's just what holding constant at 0 means starts to change depending on whether we're using a centered solution or an uncentered solution. Okay, so just helping with interpretation of this. Okay. So for our sort of model up here, right? Our multiple regression equation here is our intercept, a coefficient for pain, coefficient for opiate use, and my coefficient for PTSD. Okay, and so again, in this centered solution, we're going to have pain and PTSD centered at their respective means, right? So this is going to be the mean of pain, the mean of PTSD. But what we're going to do is I'm going to go through and I'm going to, for this data set, I'm going to center opiate use. Okay, and so literally I'm going to center opiate use the same way I would center other things, even though it's not a continuous variable. In this case, in this set that we're working with, remember our opiate use is almost like 50%, so not using and 50% using. And so when I go through and reduce, ends up taking opiate use, 0, 1 value, and subtracting the mean, which is right at 0.5. And so what ends up happening is now anybody who's not using opiates has a value of negative 0.5. Everybody who does have opiate use has a value of 0.5. And if I'm holding opiate use constant at 0, it just means I'm controlling for opiate use, right? No one actually has a value of 0. It just means I'm controlling for this dichotomous predictor, okay? But, and this is the thing, everybody look at me sort of dead square in the eyes right now. Centering your categorical predictors does not mean subtracting 0.5, right? In this case, we're subtracting 0.5 because 0.5 is sort of, it is an even balance, right? We usually won't have perfect, so what you would literally do is just take the mean of our predictor, and then we just subtract whatever the mean of sort of that dichotomous predictor is, right? We're going to get into examples. Someone will try and center their dichotomous predictor by subtracting 0.5. Don't do that. Sort of, if I go through and so I have way more people in my 0 group than my 1 group, the mean of that dichotomous variable is going to be less than 0.5. Like that's the value we need to go through and change it. So it's still a dichotomous indicator. You have negative scores and positive scores. It's just 0 means controlling for that variable. Okay. So if I go through and I regress and I sort of run this this solution, what I get is I get a value of okay. This is why these coefficients up here, these are different because I was regressing for this one. I'm regressing the natural log of pain, or excuse me, the natural log of role functioning onto outcomes. Here, remember, we're just using role functioning, so that's why we're seeing some differences in these individual coefficients. So let's ignore this so we're not confusing anybody. But if you're trying to match up and understand why you have different values for your coefficients in sort of the regression and hierarchical regression handout and the one that you've got now, recognize that on the one that we had before, because we'd screened and determined that role function was a terrible variable, log transformed it, then regress log transform role functioning on the stuff. For this one, it's just straight up role functioning, just so we don't complicate things. Okay. So if I go through and I center all 3 of my variables, I get my regression equation gives me my intercept, coefficient for pain, coefficient for opiate use, and coefficient for PTSD. Okay, so help me out. What is my intercept? Tell me.
What the value of your outcome is what?
Okay, so elaborate on that.
So
what is my outcome?
Your
Role functioning, yeah. So my expected out value of role functioning, what?
control
does that literally mean in my centered solution? Uh-huh, and what is it? Okay, so put it all together.
When pain is the source or the role functioning source.
Okay, good, right. Basically what we're saying is this intercept, this is our expected value of role functioning, holding pain and PTSD constant at their mean and controlling for opiate use, right? So it was switch it around. So intercept, we're saying, so the intercept here is expected value of role functioning, controlling for opiate use when pain and PTSD are held constant at their mean. I mean, I could say holding opiate use constant at the mean, but that doesn't actually mean anything. It just means I'm controlling for opiate use, right? But pain and PTSD held constant at the mean means something, right? We're holding these constant at the average or most representative value of the sample, right? And so in this situation, at average levels of pain, average levels of PTSD, holding opiate use, controlling for opiate use, my expected value of my outcome or role functioning is going to be 48.2. Okay. Haley, give me an interpretation of my coefficient for centered pain here.
For every 1 unit increase in pain, we expect to see a 10.71 unit decrease in role functioning, holding PTSD constant at its mean and controlling for opioid use.
Perfect. Right. Kate, help me out with my coefficient for PTSD.
So for every unit increase in PTSD, you'll see a 0.3 decrease in role functioning, holding opioid use, holding for opioid use and when pain is at its mean.
Okay, yeah, so holding pain at its mean and controlling for opiate use. Right. Amelia, you want to take a crack at opiate use here?
Would be happy to increase instead of a 1, or, I mean.
Okay, so think about this. So a unit increase could be going from 0 to 1,
Yeah.
right? But does that have to be a unit increase? What if I went from negative 0.5 to 0.5? Is that still a unit increase? Yeah, right. So how would we interpret this guy?
So, going from no opioid use to opioid use, we would have a 0.69 unit decrease in role functioning, keeping both pain and PTSD as mean.
Perfect. Again, this is just the difference in pain and PTSD. This is still going to be, even though we've changed these around, so it's negative 0.5 and 0.5. So we're not really going from 0 to 1 because 0 is not a value that anybody has and 1 is not a value that anybody has. But because going from no use to use is still a 1 unit change, right? Basically what we're looking at is this is the expected difference in role functioning, holding pain and PTSD constant at the mean, right? So again, so this is sort of going through and interpreting some of these coefficients. This is the same thing as anything that we would go through and take a look at our handouts, right? So wanting to get down in it, this starts to become important to sort of put these coefficients into literal words, and particularly if we're using metrics that have some sort of meaningful outcome, right? Again, like if sort of my outcome is weight or something like that, right? Now all of a sudden, sort of weight in pounds is a meaningful outcome, and all of a sudden these coefficients have some real interpretive meaning, right? Or I'm looking at number of convictions or something like that, right? Something along these lines. One, nice to not just have these just be numbers that just are just kind of numbers that sort of mean different stuff. Actually being able to put into words what this actually means in a practical sense, and then starting to be able to use this flexibly as we start to shift around that 0 point in terms of thinking about what things mean. Okay, so people are comfortable sort of interpreting, and so on your handout, again, remember that we were regressing natural log of row function and all this stuff, so these values are going to be different. Here, it's going to be just taking a regular row function and regressing on. Questions? All right, so if we go to, and we take a look at our, in SPSS, this is our uncentered solution. This is just regressing row functioning onto our uncentered PTSD, our uncentered pain, and opiate use as a dichotomous 0-1 indicator. And here's our centered solution, regressing row functioning onto centered opiate use, centered pain, centered PTSD. Right? So Laura, if I'm looking at this, where am I seeing differences? Am I seeing differences in my overall model? Did this change my R squared? Anything going on there? Didn't change anything. All I did was shift these around, so my model doesn't change, right? What about, Nick, my coefficients? Am I seeing any differences here?
No, only your standard error for the constant.
Only my standard, and what else for the constant? Standard error, you're right, what else?
T-value is different.
T-value is different, and what else?
The B is different.
Yeah, the coefficient, right? Because again, this is the expected value of row functioning when, for people who aren't using opiates, when pain severity and PTSD scores are literally equal to 0, right? Because in this model, this is my expected value of my outcome when all other variables are held constant at 0. Well, that means I'm talking about people who aren't using opiates, who have no pain and no PTSD, right? I'm talking about a very specific person in this model, right? And so again, I can't impress how important it is to start thinking very literally about who is this talking about? Well, this is talking about people who aren't using, expected value of my outcome for people who aren't using opiates with 0 score on pain, 0 score on PTSD, okay? But then down here, we see now my constant is shifted some, right? I'm seeing my constant is lower, and if we're thinking about what this model is doing, this makes some sense, right? Because this is my expected value of row functioning for people who have average levels of pain and who have average levels of PTSD, sort of holding, controlling for opiate use, right? And so now all of a sudden, if we're talking about not people with pain and PTSD scores at 0 and people who aren't using opiates, we're talking about people at average levels of pain and PTSD, controlling for opiate use, we would expect probably row functioning to be lower for this group of people than the other one, right? So this is what we're seeing. But my t-value, my standard error starts to change around because I'm testing whether different value is reliably different than 0, right? So we see some changes here. But if we're looking at our coefficients, right, we're seeing my coefficient for opiate use is the same, pain severity is the same, PTSD is the same, my standard errors are the same, my standardized coefficients are the same, my t-values are the same, everything is looking the same. My zero order, my partial correlations, none of this changes with my centered solution, right? This is a nice way to make sure that you've not done something wacky with your outcomes in terms of centering, okay? Do we need to center our outcome? Did I tell you to center your outcome? Simon didn't say center your outcome. Do not center your outcome variable. Don't need to center an outcome variable. That's not a useful thing. Leave your outcome variable alone unless we're sort of going through a standardized solution. We'll talk about that in a bit. Okay, questions on centering, so what that does to our model? Yes?
So there's a question on the current problem set.
Yeah.
Where we could center through the variables. Are you expecting this to be?
No,
Okay.
we hadn't.
Okay.
I didn't tell you to center anything on that, did I?
No.
Oh, you're just saying we could
You
center.
would tell us if we were to center it?
What's that?
You would tell us to center
Oh,
it?
yeah. Moving forward, you'll center your variables for doing stuff. Yeah, but
Sounds good.
you expect you to magic some stuff up. Are you saying just so you could center it because they're continuous variables?
They're dichotomous.
Oh, well, okay. Yeah, you can center continuous dichotomous variables, whatever, just making sure that you sort of know what they're talking about. But no, you don't
Okay,
need to
sorry.
go through and doing that
Thanks.
stuff. No. Yeah. Other questions? All right. So, in thinking about the idea, the thing that we're trying to get at, so we were sort of unsatisfied with our standard regression models because we've grown past them. We've moved beyond just our standard multiple regression models. And what we're interested in is whether or not, in our moderation question, whether or not changes in one variable start to impact the strength or magnitude direction of other variables in the model, right? So our one question here, what's the relation of opiate use on functioning at different levels of pain and PTSD, right? Because we've got kind of two moderating questions. What's the impact of opiate use on the relation between pain and functioning, and what's the impact of pain on the relation between PTSD and functioning, right? And so this is our model, right? Let's go through, and so my question is, what's the relation of opiate use on functioning at different levels of pain and PTSD? Well, let's go through and start plugging things in and see what happens, right? So what I've got, I want to say, what is the relation of opiate use with functioning, specifically if I'm looking at high levels of pain and high levels of PTSD, okay? So let's take our model. So here's our sort of regression model, and let's plug in values for high pain and high PTSD, okay? So for here, because we've centered our models, 0 is our mean, right? High and low, we're just going to use a standard deviation above and standard deviation below. So a standard high pain, if we're calling high pain a standard deviation above the mean, that's just 1.34 because our standard deviation is 1.34. Low levels are negative 1.34. Centering kind of made that easy, right? It's just plus or minus, right? Standard deviation below is a standard deviation below the 0, so it's going to be negative. Standard deviation above, right? So high PTSD, low PTSD. High PTSD, standard deviation above, 19.76. Low PTSD, standard deviation below, negative 19.6. No opiates, negative 0.5. Opiates, 0.5, right? People see where we're getting these values. Okay, we're just taking a standard deviation above and below. This is a nice thing. Starts to, instead of saying, here's the mean value is 40, and now a standard deviation above is 5, so it's 45, and the standard deviation below is 35. Starts to get bulky, right? When we centered it, right, the mean is 0. Standard deviation above is just plus, standard deviation below is minus. Makes it nice, right? So let's go through, and so what I want to know is I want to see whether or not high levels of pain and high levels of PTSD change the nature of the relation between opiate use and my outcome, okay? So I've got my regression model, and I've plugged in high levels of pain, right, which is 1.34, high levels of PTSD, 19.676. You'll see what I did here? Follow me? Okay. Well, then we can go through and we can just start running this out, right? If I go through multiply this, and reduce this down, I get a value, relation between opiate use and role functioning is negative 0.69, right? And so then if I go through and I put opiate use and no opiate use, my expected value of role functioning for people with no opiates at high levels of pain and PTSD is 29.6, and people who are on opiates with high pain and PTSD is 28.96. Okay. People see what I did there? Okay. Okay. So, but what if I want to say, what's the relationship with opiate use and role functioning for people who have low pain and high PTSD, right? So the same thing, if I take my regression equation, high PTSD here, low pain here, and I go through and I sort of multiply these, go down. Now I'm at 58.01, 0.19, negative 0.69 opiate use. And so for people with no opiate use, 58.36, opiate use 57.67. Okay. Did it matter if I was putting pain in whether I'm talking about high levels of pain, PTSD, low levels of pain, PTSD? What did this do to the nature of the relation between opiate use and role functioning? What did it do to my coefficient, Evelyn? It changed my coefficient here? No, my coefficient is still negative 0.69. Right? Who's got a calculator? Layla's got a calculator. Layla, take 29.65 and subtract 28.96. What'd you get?
Sorry.
Yeah, negative 0.69. Yeah, take the 58.36 and subtract 57. We get 0.69, right? So it didn't matter, right? We're substituting high levels of pain, high levels of PTSD, low levels of pain, low level, but it didn't change the nature of the relation between there. So we're swapping other values around, but it didn't do anything, right? The difference between people taking opiates and people not taking opiates is the same no matter if we're swapping in higher or low levels of pain, right? So it didn't do anything, right? So what's the impact of high levels of pain, different levels of pain and PTSD on the effect of opiate use and role functioning? Nothing. It didn't change it around, right? We can do the same thing. What's the relation of PTSD to functioning at different levels of pain and opiate use, right? What if we start swapping that around? So again, here's our model. So let's substitute pain